Just after 8 on a January morning, steam pressure is falling in a 30-story building. One of the boilers has stopped firing. Hundreds of offices are calling for heat. The outside air is below freezing, and the engineer watching the gauges makes a decision that nobody upstairs will ever know about. His first responsibility is to tell the building no. The boiler does not go cold at once. That is what makes the moment deceptive. Steam is still sitting in the header. Hot pipes are still carrying heat upward. Radiators and heating coils are still warm. To everyone stepping out of the elevators, nothing appears wrong. The skyscraper looks automatic. It is not. The engineer can already see what will happen next. Steam pressure is beginning to fall. Ventilation fans are pulling freezing air into the building and warming it before sending it upstairs. The morning load is rising exactly when one of the machines producing that heat has taken itself out of service. A low-water control stopped the burner, and forcing fire back into a boiler before understanding why can turn a comfort problem into a mechanical emergency. So while the pressure keeps falling and 30 floors grow colder, the engineer checks the gauge glass, the feedwater system, the pump indicators, and the control that caused the trip. Thousands of people work beneath fluorescent lights, ride automatic elevators, make telephone calls, and never once see the mechanical plant that makes the building habitable. But in the basement, engineers listen to pumps, watch boiler pressure, adjust valves, maintain air conditioning machinery, and wait for the small change in sound or gauge reading that means something large is about to fail. The day shift begins before most office workers arrive. The engineer comes through a service entrance and changes into work clothes. His job title is stationary engineer. The word distinguishes machinery that stays in one place from engines that travel. The equipment remains fixed. The engineer may spend the entire shift moving between it. A 1963 U.S. Department of Labor handbook described stationary engineers as workers who operated and maintained equipment used to generate power and to heat, ventilate, and air condition buildings. Their machinery included boilers, refrigeration equipment, pumps, compressors, and the increasingly complex control systems connecting them. Office and apartment buildings employed thousands of these men. In a large skyscraper, he may not work alone. There can be a chief engineer, assistant engineers, boiler operators, and maintenance crews. Shifts run around the clock. The building never stops needing mechanical service. A night engineer may work in a nearly empty tower with fewer complaints but far greater isolation. If equipment fails at 3 in the morning, he has to know what he can safely restart, what can wait until daylight, and when the problem is serious enough to wake someone at home. The outgoing engineer does not simply leave. He reports what happened during the previous 8 hours. Boiler number 2 has been cycling more often. A pump bearing sounds slightly rough. One tenant complained the northwest corner was cold. Then the incoming engineer opens the logbook. Long before computerized building management screens, that book is one of the building's memories. Boiler pressure, fuel use, temperatures, equipment runtime, repairs, and anything unusual get written down, because one reading means very little without knowing what the machine normally does. Then he begins his round. A 1960s mechanical room does not resemble the office tower above it. The air is warm, heavy with the smell of steam and oil. Equipment hums and clanks. The boiler sits at the center of a continuous loop. Fuel enters the burner. Heat transfers into water. Steam leaves the boiler and travels into the building. And after giving up its heat, much of that steam condenses back into water and returns. Feedwater equipment sends that water back into the boiler to replace what has become steam or been lost from the system. The engineer checks steam pressure, water level visible in the gauge glass, fuel conditions, and the flame where inspection is possible. Then he moves to the pumps, looking for leaks, overheating, vibration, and changes in sound. This is why he walks the plant. A control panel can tell him a motor is running. His ears may tell him it should not be. Water level is critical. Steam is constantly leaving, so water has to be maintained at a safe operating level. Low water cutoffs and feed water controls existed to prevent firing when the level became unsafe. By the mid-1960s, boiler control systems could feed water automatically and stop the burner if a low water condition developed. But automatic did not mean foolproof. A float could stick. A line could clog. A pump could fail silently. A gauge glass could give a false reading if its connections were obstructed. Water quality is another invisible job. Every gallon circulating through a boiler carries minerals or dissolved material that forms scale, promotes corrosion, or becomes increasingly concentrated as steam leaves. The engineer tests boiler water, adds treatment chemicals, and removes some water through blowdown when necessary. Scale is not merely dirt. It acts as insulation between heated metal and the water meant to carry that heat away. The metal overheats. Tubes can fail. In extreme cases, a boiler can rupture. So some of the engineer's most important work produces nothing a tenant can immediately feel. A water sample, a chemical adjustment, a carefully controlled blowdown that prevents a failure 3 months from now. As the city wakes, the mechanical load changes. Fans start, pumps circulate, heating coils receive steam or hot water. Outside air begins entering the ventilation system, and on a bitter morning, that air has to be warmed before it reaches occupied space. The engineer watches the load rise through the instruments. Pressure that was stable overnight begins falling as more steam valves open upstairs. The burner responds by increasing its firing rate. Combustion controls adjust fuel and air, but the engineer watches the result rather than simply trusting the mechanism. Then the telephone rings. A secretary on the 22nd floor says her office is freezing. The engineer does not immediately raise boiler pressure. A cold office can have dozens of causes, and the boiler may be fine. A thermostat may be wrong. A control signal may have failed. A valve may be stuck. A damper may not be moving. A heating coil may not be receiving flow. An open window can defeat the system locally, while every gauge in the basement looks normal. In many commercial buildings of the era, pneumatic controls carried commands through small air lines. Thermostats and controllers used changes in air pressure to position valves and dampers. A leak in one of those air lines, too small to hear, could leave a valve stuck or a damper unable to close, making one office freeze, while every instrument showed the system working correctly. The stationary engineer learns to think in systems. If only one office is cold, he suspects the branch serving that area. If an entire floor is cold, he looks farther upstream. If the whole building is cold, he looks hard at the central plant. That hierarchy keeps him from adjusting a healthy boiler because one person on the 22nd floor opened a window. By mid-morning, the building is fully occupied. Elevators move constantly. Lights, office machines, people, and sunlight add heat to interior spaces. The problem that dominated early morning begins reversing. The sunny side of the building may grow too warm, while shaded offices still need heat. Interior zones, spaces with little exterior wall but plenty of people, lights, and equipment, can require cooling even on a cold day. It seems wrong, running refrigeration machinery while the boiler is firing, but those interior rooms have no windows to shed heat, only sources adding it. Air handling systems mix outside and return air. Heating and cooling coils condition it. Fans push it through ducts and risers. The engineer is not merely heating a building, he is balancing demands that disagree with one another. And every piece of equipment creates a new way for the system to fail quietly. One afternoon, the chilled water temperature begins rising slightly. Nothing dramatic, half a degree, maybe less. But it is moving in the wrong direction, and the engineer notices. He checks the refrigeration equipment. Compressor is running. Condenser water is flowing. Then he listens. There is a sound that should not be there, subtle enough that it might have gone unnoticed for days. A bearing in one of the pumps is beginning to fail. He does not wait for it to seize. He brings the standby pump online, isolates the failing unit, and writes it in the log. Upstairs, nobody's office got warmer. Nobody called to complain. The repair happens during a scheduled maintenance window 2 days later. The failure that never occurred is the job done correctly. The boiler tripped just after 8. Steam pressure has been falling for several minutes now. The engineer has checked the water gauge. The level is low enough to explain the trip, but it has not disappeared from sight. Now he has to discover why it fell. The feedwater pump that should be supplying the boiler appears to be running. At least its motor indicator says it is. He moves closer and listens. The sound is wrong. The motor is spinning, but the pump is not moving water the way it should. A coupling problem, perhaps, or a blockage in the line. The plant has a reserve pump. He brings it into service and stays beside the system, watching. The water level begins returning toward its normal operating range. He does not assume the problem is solved. He watches the level. He verifies the flow. He checks the low water control to ensure it will permit a restart. Only after the boiler has a safe water condition and he understands what caused the trip does he begin the restart procedure. The burner sequence purges the furnace, establishes ignition, proves flame, and returns the boiler to service. But restoring flame is not the same as restoring the building. Steam pressure has fallen, and dozens of floors are still taking heat from the system. The boiler cannot instantly replace everything that has been consumed. The engineer watches the burner increase its firing rate, watches the water level as steam production rises, and watches the second boiler closely, because one failure is the worst possible moment to ignore the machine still carrying the load. Upstairs, almost nobody knows any of this happened. Perhaps a few offices stayed cooler than expected for 20 minutes. Perhaps someone called building management. Then the pressure recovers, steam moves normally through the system, and the red light remains dark. The engineer is not finished. He records the event in the logbook, the time the trip occurred, the observed water condition, the pump changeover, the boiler restart, and the equipment that now requires inspection before the next shift. To someone upstairs, the achievement was getting the heat back. To the engineer, the more important decision happened before that, refusing to make heat until he knew it was safe to do so. Many cities and states treated stationary engineering as licensed work because the machinery in a large mechanical plant contained enough stored energy to injure far more than the person standing beside it. In 1963, the Labor Department reported that 8 states and more than 50 cities required stationary engineers to be licensed. License classes could restrict the steam pressure or horsepower of equipment a worker was allowed to operate. Higher pressures stored more energy and created more danger if something failed. The route to the job often took years. Many engineers started as helpers or boiler operators. Formal apprenticeships commonly lasted 4 years and combined hands-on experience with mathematics, physics, chemistry, blueprint reading, applied electricity, refrigeration, ventilation, and heating theory. That training explains why the engineer is more than someone who knows which switch turns the boiler on. He is expected to understand why the switch should be on and when it should not be. When a gauge disagrees with a thermostat, he decides which reading makes sense. When 2 pumps behave differently, he recognizes which one is failing. When an automatic control begins hunting back and forth instead of settling, he considers whether the problem lies in the control system rather than the equipment being controlled. Over time, he learns the building almost like a physician learns a patient. He knows which riser serves which floors, which pump feeds which loop, which valve can isolate a section for repair, and which piece of equipment can be taken offline without losing service to the entire tower. After years in one building, he knows how the plant sounds early in the morning, how quickly pressure falls when the weather changes, which valve becomes troublesome every winter, and which pump vibrated differently after it was rebuilt. The skyscraper becomes familiar, not as architecture, but as behavior. By afternoon, the building has forgotten the morning trouble. That is success. There is no applause when pressure stays normal, no letter thanking someone for preventing a failure, no award for keeping water exactly where it belonged. Yet the occupation provided real status within the mechanical trades. Experienced engineers with higher grade licenses could advance to chief engineer or building superintendent. In 1962, the Labor Department noted large regional differences in wages and reported that men responsible for major operations could earn considerably more than standard stationary engineer rates. The work carried respect among people who understood what it required. Automation did not eliminate the stationary engineer all at once. It changed what he watched. Pneumatic controls gave way to electronic sensors. Computerized building management systems began monitoring equipment that once required constant human observation. Remote alarms could summon help when conditions became abnormal. The Labor Department could see this direction in 1963. It expected demand for stationary engineers to continue, but warned that more automatic and centralized equipment might limit employment growth. Routine manual adjustments decreased, but the central question remained: what do you do when the automatic system behaves incorrectly? The modern building engineer may have a screen displaying hundreds of readings. The 1960s engineer stood in front of gauges and walked between equipment. Beneath both systems lies the same discipline: know what normal looks like, notice when it changes, and understand what can safely wait and what absolutely cannot. At the end of the shift, another engineer arrives and the handover begins again. The boiler tripped during the morning rush. The standby feedwater pump is now carrying the duty. The original pump needs a coupling inspection. Pressure recovered, and no further low water condition occurred. The incoming engineer adds those facts to his own mental picture of the plant. The day engineer changes clothes and leaves through the service corridor. Upstairs, office workers are riding elevators toward the lobby. Many have spent their entire day dozens of floors above the mechanical room. They saw glass walls, polished stone, fluorescent ceilings, and a skyline view. The engineer saw pressure and temperature, flow and vibration, the small symptoms that precede large failures, and the gap between what a gauge says and what a machine is actually doing. In the basement, the evening shift checks the same instruments, listens to the same equipment, and opens the logbook to read what happened that morning. One line near the bottom of the page: boiler #2 tripped 0817, low water, standby pump online, service restored 0843. 30 floors that never grew cold, 10 words that nobody upstairs would ever see.